Participants. Good morning, sir. Good morning to Dr. Ramalinga Swami, sir. I request Dr. K. Anupriya Madam to introduce the resource person.
Thank you, Sherwani. Am I audible?
Yes, ma'am, it's audible.
Yeah. It gives me great pleasure to introduce our resource person, Dr. Ramalinga Swami Cherku. Currently, sir is working as an assistant professor in the Department of CSE at NIT Warangal. His research interests are soft computing, optimization, deep learning, ANN, machine learning, bio and nature-inspired algorithms for wireless sensor networks, data mining, and fuzzy logic. Sir published more than 16 journal articles in well-reputed journals and more than 12 conference proceedings. Currently, Sir is guiding 2 research scholars in the computer science discipline. Dr. Ramalinga Swami Cherku received Venus Young Faculty Award in the year of 2019. Sir also organized various workshops, STTPs, conferences, and webinars. We are honored by your presence, sir. Thank you. Now I request Dr. Ramalinga Swami Cherku to take over the session. Over to you, sir.
Thank you, ma'am. So, it's a very good morning to one and all. And so today I'm going to discuss about how we can make use of these soft computing techniques, or strictly speaking, these bio-inspired algorithms for the rule-based classification algorithm. So before I will start the talk, and let me give the background of why we are preferring to use the rule-based classification algorithms, and how they are better. What is the advantages of this rule-based classification algorithm and compared to the other state-of-the-art algorithms. So then we will move on to so how can we generate those rules with the help of these soft computing or bio-inspired algorithms. Okay, so let me start my talk with the overview of the rule-based classification algorithm, why people are started using this what you call the rule-based classification algorithm. Okay, so in my talk, most of the time I will use the whiteboard. So if required, I will switch over to the PPT slides. Okay, so the most of the talk will be switching over between the whiteboard and what you call the PPTs. Okay, so let me start so let me share my screen then. Yes, I hope you are able to see my screen. So can anybody confirm? Are you able to see my white screen, whiteboard?
Yes, sir.
Okay, thank you, ma'am. Yes. So traditionally, we can most of the times we will use this ANN based classification algorithms. Okay, ANN, the artificial neural network. So earlier we will use some statistical classifiers. So then we move to the artificial neural net based classification algorithms for the classification task. So I hope you know what is the classification and the regression. So if you see, these are the classification and the regression. These are the supervised learning task. Okay, these are supervised learning models or methods, whatever you call. Why it is called the classification and regression is a supervised learning task is, so if you take any machine learning model, the input for any machine learning model is in a data, something called raw data. Okay, in machine learning terminology, it is called data set. If this data set is having, if the data set is having an extra information like ground truth information, so with the help of this ground truth information, if you train this model, on the basis of this ground truth information, if you train this model will rectify their errors and try to minimize certain loss function and try to learn the knowledge which is there in this raw data in the training process. So this training process will help us to gain the knowledge, okay? So intelligence, some sort of intelligence with the help of this ground truth information. So the presence of this ground truth information, or sometimes we'll refer as a class label, will help us to train your model very effectively, and at the end we will get some knowledge which is there in your raw data. So as we are training our model with the data which is having the ground truth information, so this ground truth information will act as kind of supervisors, kind of instructor to guide your model to achieve or to learn the knowledge, like how your mother used to teach you when you are in childhood. Suppose if you are touching in a ball, so your mother used to tell this something, you instead of ball you are touching wrong thing, then your mother used to instruct that is not the ball, this is the ball. So kind of guidance. So that is called guidance, some ground truth information. That's why these models which are developed on the basis of this ground truth information is called supervised model, and the classification algorithms are these classifiers all come under this category. Even the regression models will also come under this category. And so the difference between the classification and regression is, in case of classification, the output, the class label which I mentioned, the ground truth information, the ground truth information is in a discrete quantity. But where in the regression, it is in a continuous quantity. That's the only difference. The ground truth in the classification problem is a discrete quantity. Like if you say whether you are having COVID positive or negative, or whether will they return tomorrow, yes or no. So given a pattern, it should belong to either S class or no class. You have to classify to any one of this class. But where in the case of the regression, it is in a continuous quantity, something like your temperature or stock market prediction. So if this stock market prediction, suppose what could be expected? The stock price of HDFC Bank, suppose it could be something 1024.3. It is a continuous quantity. You know what is the continuous? There exists every possible value for every. So there exists every possible value in the discrete quantity. So there is no intermediate values. It belongs to that category or that category. So your temperature could be 1 or 2 degrees or something, 42 degrees, something. There exists every quantity in the continuous. If it is a continuous curve, there exists every possible value in a specific range. So this is some how the classification regression are classified as supervised learning models. So toward this end, the classification or regression task, we started using some kind of statistical classifiers very beginning of this, maybe in the 1980s. Then by the invention of this artificial neural network, people started using ANN as a classifiers. So we can make use of ANN as a classifier. So when I want to make use of ANN as a classifier, so you know what is ANN, I think, okay, see? So let me go back. So if you take a typical ANN, there are the very basic ANN will have 3 layers, the very basic ANN. So this is called input layer. So this is called hidden layer, and this is called output layer. Output layer, the very basic ANN. The very basic ANN will consist of at least one hidden layer. And these neural networks will connected in some fashion. Suppose they have some interconnections, something like this. Between successive layers, there is interconnections, right? So when I given, this is my ANN model. So when I given any data, suppose if there is a raw data, so this raw data is having some class label. ground truth information, and this is our raw data. Okay? And this raw data is with class labels. Okay. If this data is given and you train this model by using some training algorithm, I'm not discussing what kind of algorithms and all, and your objective is you have to classify. So whether it belongs to this class, suppose it's a class 1, this is class 2. Something S class or no class, diabetes positive or negative, something like that. Right. Now, if you see, after training is once you finish your training by using some training algorithm, your model has finished training. Yes. So as I mentioned, once your model has finished training, it acquires some intelligence. It acquires some intelligence or some knowledge from raw data. To gain the knowledge from raw data, we train your model. So that is the idea. Yes, I'm assuming that training is finished and my model has learned some knowledge. Right. But where is this knowledge? So if you see in typical, this knowledge is in the form of weights. So if you see that every layer in here will have some weights, W1, W2, the every interconnection will have some weights. So these weights are getting adjusted to minimize the classification error. Right. So when for which set of values of these weights your loss, your function, your error is minimum, so that we call as the perfect match for those for fine tuning process, the perfect match for those weights. So the whole idea of this training is to adjusting the weights. Train the model means adjusting the weights. But these weights will represent your knowledge. So if you interpret these weights, you cannot interpret these weights, because if you want to see the knowledge, I want to look at the knowledge, but the knowledge in the form of the weights, but you cannot interpret these weights. By looking at these weights, you cannot interpret anything. It is some weight matrix. Okay. So the input weight matrix, weights between input layer to output layer, weights between the output layer to hidden layer to the output layer, and hidden layer to the output layer, something. So there are some weights, some weight matrix. So by looking at this weight matrix, we cannot interpret anything. So that is the reason people started using a rule-based classification. Algorithms are called rule-based classifiers. So this is a problem in ANN-based classifier. Then people have used. So then after ANNs, so after statistics, then ANNs, then we started using rule-based classifiers. So that was the idea behind why people are preferring to use rule-based classifiers, because in rule-based classifiers the knowledge is interpretable. Why? Because the rules there are in rule-based classifier, there are rules in the form of if something, then this. So there are the rules are if then shape. So we can easily understand these rules, and you can interpret this knowledge which is gained from your raw data. But where in the case of ANN based classifiers, we cannot interpret, so you simply have a weight matrix. By looking at, by glance over that weight matrix, you cannot interpret anything. So that is the reason people have used the rule-based classification algorithms. Okay, so toward this end, when people have started using rule-based classifiers, so in the literature, so there are already existing rule-based classification algorithms are there, like C4.5, CORT, ID3. So there are some few C5.0 something. These are the few the rule-based classification algorithms. Right. Now let's have some idea how these algorithms are generating the rules. Once the rules are being generated, then how can we generate the same set of rules which are being generated by these algorithms with the help of bio-inspired algorithms? So for this, so let us talk about how we can generate rules from these the traditional or state-of-the-art rule-based classification algorithms. So if you look at any one of these, the idea is first they will construct a tree. If you take any one of this algorithm, first they will construct the tree. The second step is the rule generation. If you take the overall, the idea is, if you take any one of this algorithm, the rule generation, how the rules will be generated? Traverse from root to leaf node. So just traverse from the root to the leaf node. Traverse from root to leaf. This is the rule R1. This is R2. This is R3. R4. Now, question number of rules is, now can anybody tell number of rules? Number of rules is equal to the number of leaf nodes in tree. So how many number of leaves are there? So that many number of rules will be there. This is R1, R2, R3, R4, 5, 6, 7, 8. Something in this case 8. Right. This is in a high level view how rules were generated. First you have to construct the tree, and then you have to traverse this tree from the root to the leaf to generate the rule. So this is a rule generation process. It's common. So this is common. But only thing is, only we can differ, the each and every other where we can differ is the way you will construct this algorithm. Way of the constructing this tree. Right. And I want to discuss something about this trees. So in this tree, the root and internal nodes are the features. So what is the specialty of this tree? The roots and internal must be features, and leaf nodes must be ground truth or class labels. So let me show one. Yes. So if you see, this is one simple. Are you able to see? We see here, this is one internal node, this is one internal node, this is one internal node. And if you see the ground truth information, the leaves are the class level, the S class, no class, no class, S class. The leaves are the class labels, and internal nodes and including the root will be a features. And of course, it's not simple feature. So there is some condition. So we will create some condition on top of this feature, but the idea is the internal should contain the only features. You may have the condition or a feature, right? Now, how can we construct this decision tree? Because once you construct this, once step 1 is done, once you construct the decision tree, you can generate the rules very easily. But each and every algorithm is differ in the form of the way you will construct the decision tree. So let me give how we can construct this tree. Suppose the overall idea is, first you take the whole data set. First you will take the whole data set. So what we are trying to do, we are trying to partition my data set. I will try to partition my data set with respect to certain condition. By keeping some condition on feature or, so one second. Yes. Sorry. So the overall idea is just I will take the whole data set, then I will start tweaking this my feature. You take one of the feature, like suppose there are features F1, F2, F3. This is the class labels here, the ground truth information. So what I'm trying to do, I will try to keep a condition on top of this feature. So once you filter, like kind of filtering, so once you keep some filter or some kind of condition on top of the feature, so what you will do, you can segregate your, you can partition your data set, something like this. Then you will partition this process. Then you will do this again partition by keeping some condition on feature. Condition on feature, okay, something like this. Yes. Till how long you have to do this process? Till how long you have to do this process, okay? So till you have to do this process, this iterative process, this recursive process, till the entire subtree, the entire this partition will have same class label. Will have same class label. Suppose if it's all are having same class label, so then till that you have to do. So if that means that if all the samples will have the same class label, it means that it is a homogeneous partition. It is called homogeneous partition, and if that partition is there, we can say that that node we can consider as a leaf node, and the class label of that leaf node is the class label of which is assigned to all the labels, right? Because all are having same class, all are having COVID positive, COVID positive, COVID positive, then this is a positive class. You can assign the positive class label to this particular partition, right? So this way you have to generate what you call a tree structure. So this tree has some peculiar name called a decision tree, because this tree will help us to make certain decisions. Because when you're traversing from the root to the leaf, you will come to one decision. Like decision means you can classify whether a sample is positive class or the negative class. So that's the reason this tree is called the decision tree. Yes. Now, the way you will generate this decision tree is different from algorithm to algorithm. So we have listed out 3 algorithms called ID3, C4.5, and it's called COT. If you take any one of this algorithm, the approach is overall is same, but the way you will differ the each and every algorithm is how do you select these features? How do we select best condition for feature? So this is called splitting attribute. The feature is called your splitting attribute. So how do we select best splitting attribute? A best feature for splitting. So what is your idea of splitting? So once you split it, it should create homogeneous cluster, homogeneous partitions. So the idea is you have to create homogeneous partitions, and for that you have to choose this your splitting attribute. How do we select the splitting attribute? Means this is a splitting attribute. The splitting attribute means what is the condition over on this top of this what is the best condition for a given feature, something like that. Something like age is greater than 50 or age is greater than 40. Which one is correct? Okay, which one I have to choose? Age is 45, age is or splitting attribute. This is a splitting attribute, and this is a condition on splitting attribute. Now how do we select? So for that we require some measures. So these methods called splitting attribute measures. So we have a few such splitting attribute measures called entropy, Gini index, and information gain. So depending on the which splitting attribute we will use, based on the structure of the decision tree will vary. So different algorithm will use different kind of splitting attributes. That's the only difference between all these three a decision tree algorithm or rule-based classification algorithms. So depending on some algorithm will use entropy, some algorithm will Gini index, some algorithm will use information gain, something like that. But overall, the idea was this: they will take the data set, they will split this data set recursively till they reach homogeneous partitions. Right? So if you change the measure, accordingly the structure will of the decision tree will change, and of course this in turn will lead the what you call the rules will also change. Right. Now, so this is the so far. So we have seen how the rules were generated with the help of decision tree. And once you construct this decision tree, the rule generation process is easy. Just you have to traverse from root to the leaf node to generate the rules. Now, right? Now let's see how we can make use of how we can generate these sort of rules using bio-inspired algorithm. So that is the idea. I think that is our topic for today. Right. So if you see how we can use the bio-inspired algorithm for generating the rules are called, strictly speaking, classification rules. Okay. So let me give the high level view, then we will move on to the specific problem, how we have generated this classification rule with the help of spider monkey algorithm, one of the bio-inspired algorithm, a nature inspired algorithm. If you see, if you understood, we have taken the data set. Now what we did, we have identified a suitable splitting measure, and this measure will help us to assess what is the best homogeneous partitions. So toward this end, what we did, so how we can formulate this problem with the help of bio-inspired algorithms. First you have to model your problem, right? Suppose there is a data. There is a data with certain features. There will be F1, F2, and F5. There are 8 features. This is a class label, right? And I'm assuming that there are some positive classes or some S class, and S class. Some are the no classes. No, 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 no. Something like this. I'm calling this is all tuple belongs to no class. These are all belongs to S class. This is a class label. Okay, this you know. Now, if at all, if I want to attempt this problem using bio-inspired algorithm, so first you have to model it, okay? So this is called a modeling. See, in this modeling process, so what we can do is you have to choose the features. You have to choose the features. You have to choose the features which are as a part of, which are in the part of, if you know that there is a if, then if in the if part there is a conditions, if you look at any rule, and the then part you have the class information. One second. Right. So in the if part you have a condition part, in the then part you have the class information. One second. Sorry. So in if part, you have a condition on top of the features. If you look at, let me show one sample rule. I will show one sample rule so that you will come to know how a rule look like. If you see the rule over here, not here, this one. Yes, not this one. Yes. If you see, the features are something like this. If something in the glucose is the features, and so there is some lower and upper bounds, and there's a condition on top of your features, and there are multiple features involved in the part. So we can have in the part the condition on multiple features, and these features will be combined and with the help of AND operator, of course. One second.
So your screen is not visible.
Sorry. So there are sometimes we may have the features, multiple features will be take part in the if part, so in the condition part. So you have to combine these features with the help of AND symbol. Okay, and the question is, which feature is it will take part in the if part? You have to encode with the binary encoding. So if this particular feature is 1, it means it is a taking part in the if part. If this is 0, it is not taking part in your if part. So it means this particular bit is called flag bit. So this will help you to identify which are features are taking place in the if part. Right. This is okay. Now, if any feature is there, so you must specify the condition. You have to specify what is the condition. The condition typically will have less than or greater than or equal to symbol. Suppose if I am taking age between 45 to 25, something, this is the condition I want to represent. Age is the feature. So if this is 1, means this age is the feature will take part of if part. And so how do you specify this condition? So this you can specify by using the another 2 variables called lower bound and upper bound. So something, this is a feature. So this is a lower bound of that feature and upper bound of that feature. It means that every feature is represented in an encoding part as a triplet. As a triplet, if you are representing every feature as a triplet, the first field is the flag, and this is the lower bound, and this is the upper bound of that feature. So once you represent every feature as a triplet, then the same thing you can interpret in an if part. Okay, so what are in wherever the 1 is present, that feature is a taking part in our if part in a if condition, and if it's 0, we have to ignore it. Now this is fine. So now we have encoded. Now we have encoded the if part. Where is this blank? So we have done this part. But what about this? The class label information, class information. How to get this class information? So for that, what we have to do is, so you have to generate the rule from the yes class data or positive class data. So if at all, if this data is there, if any rule is being generated from this data, the class label of the data is must belongs to that class. Means suppose you have a S class data, and you have to, once you have a data, you have to segregate into this is S class data and this is no class data. Suppose for a simplicity purpose, if any rule is being generated, the class label of the rule which is being generated from this is the S class. It means that this then part is fixed. How we have fixed? So for this, to fix this, we have generated the data from positive class to decide then class as S. If any rule is generating, then the class is no. How? If any rule is being generated, if any rules is generated from this S or no part, the same thing, the class label of that data, which is being the class label of that rule, will be same as the from which data your rule is being generated. Right. So now we have successfully encoded how we can generate a sample rule. So if you encode your rule as a triplet, and one of the field is representing flag and other field is representing a lower and upper bound. Right. The first, the modeling is done. So this modeling will help you to map your problem, mapping of your problem to specific algorithms, specific bio-inspired algorithms. Means now you have modeled your problem with the help of a triplet, something like this. And now this encoding part is very, very crucial if you take any bio-inspired algorithm, because so this is actually you're trying to address you're trying to your specific problem with the help of this modeling, and so that your bio-inspired algorithm will understand this and try to solve your problem. Just kind of mapping your problem to your bio-inspired algorithm, just like something like that. How your address. So here onwards, your bio-inspired algorithm, it can be any algorithm, will start attempting to solve your problem, because you already mapped your problem in the specific format in which format your bio-inspired algorithm will understand. In that format, you have specified your problem. That's it. Right. The question is, so in the process of this solving your problem, so you have to identify the best solution. Best solution for your problem. So modeling is crucial. Then the second crucial point, if you take any bio-inspired algorithm towards any task, is you have to assess the performance, the quality of the solution. So for that, you require some fitness or objective function. So if you take any problem and you want to address with the help of the bio-inspired algorithm, so what are the things you have to do? If there is a problem, there are n number of problems we can solve using bio-inspired algorithm. So if I want to, you have to first do the modeling. The second important thing is selecting appropriate fitness function. Because when you change this fitness function, the overall quality of the solution, the kind of solution you will get is also varying. So selecting the appropriate fitness function is also important. Right? Now, what is the problem we are addressing over here? The problem we are addressing over here is the classification rule generation process, classification rule generation. To address this problem, so I have designed a modeling technique called the each feature is representing as a triplet. Now the next step is, once you've done the modeling, then what is the next step? So in the next step, you can do it by selecting the appropriate fitness function. Right? So this is what we did during our PhD, and so let us discuss about how we have generated. This is a high level you have given. Now let us talk about how we have generated the classification rules for diabetes classification. Okay, let's see that. Okay. Yes. Okay. So we have generated the reason for why we have preferred to using this the spider monkey algorithm for the generating of these rules is, so by the time when we are proposing the spider monkey algorithm for the rule mining, the people already attempted using genetic algorithm, particle swarm optimization, and artificial AB colony, but on this for the diabetes classification. But what we observed is that all of them are failed to produce the good efficient rules, efficient or compact rules, you can say. So how can we measure the performance of any rule-based classification algorithm? In the rule-based classification algorithm, we have to focus not only performance in terms of accuracy, we should also focus on the size of the rule, the size of the rule set. So means what is the length of the rule and what is the size of your rule set, how many rules are being generated. That is also an important parameter when you are doing the comparative analysis. So we found that the most of the algorithms which have been proposed with the help of GA, PS, ABC, so all of them have failed to produce the crisp rules. What is the crisp? Very compact rules. Right. Now, so what we did to generate this crisp rules, we choose this the latest algorithm was the spider monkey that time, and we have modeled the problem for the spider monkey. The given classification rule generation problem we have modeled with the triplet concept. Then we try to generate the crisp rules, and we have succeeded by providing by introducing a new novel fitness function, and we got a good results too. Let's see. Okay, so this was the modeling process. This is very important, or sometimes called encoding process. It's a very important, a very crucial step for any bio-inspired algorithms to map any problem to the bio-inspired algorithm, which the particular bio-inspired algorithm easily understands. So every algorithm will understand the problem in specific manner. So you have to first decode your problem in that way. Then your algorithm will start understanding your problem, and once it's understanding your problem, you can assess the quality of the solutions for your problem. So how do you assess the solutions? Okay, so for that you have to use some kind of object or fitness function. Okay, so here we have used the triplet concept. So where the triplet, the first feature will represent the flag bit. If it is a 1, means it is a part of your if, and if it is a 0, it is not a taking part of in the if part and the condition part. And the second subfield of this is the lower bound of the field feature, and the third one is the third subfield will represent the upper bound, means the flag bit and followed by the lower and upper bounds. Okay, so that every feature is encoded like this. So means if there are 8 features, there are 24 such subfields will be there in your encoding schema. Right. Suppose towards our specific data sets, we have took our diabetes, P minor diabetes data set, and toward this data set, we found that there were 8 features. So hence, those 8 features were encoded with the help of 24 subfields, because 8 into 3, 24. So this is the sample how I presented. Okay, so there are 8 features like pregnancy count, glucose, diabetes, diastolic blood pressure, thickness, and what you call insulin, and the body mass index, and pedigree function of the and age. There are 8 features were there, and these 8 features were being encoded like this using 24 subfields. So if you see in this the sample encoding example, so there was a 1 present in the flag bit for only the pregnancy count and the DBP. The remaining fields, the 0 were there. The same, so if I interpret this in the form of the rule is means the pregnancy count and the DB will take part in the if part, in the conditional part, and there are 2 features are there. This we can combine using what you call is end operator, right? So this, as the pregnancy count and the DBP are the one present is there, so we have taken the 3 less than or equal to pregnancy count and less than or equal to 10. The same rule can be interpreted like this. So the pregnancy count is between 3 to 10, something like this, and DBP diastolic blood pressure between 62 to 84. Then we can say that the class label is negative, because so when this particular rule was generated from the negative data, obviously the class level will be the negative. Okay, right. So this is the overall the rule generation process. So the first we model the problem in this manner, then we have to apply your spider monkey algorithm, which is one of the latest algorithms. So for the solving of this problem, so what we did, so every time, so we name this particular as a SM rule miner, spider monkey rule miner, and every time the spider monkey rule miner generates a set of rules and evaluates its fitness using training data and choose the best rule that corresponds to the maximum fitness. Obviously, so So when we are training our model, when you are selecting the best feature out of from this data, so always you look for the encoding schema which is corresponds to the maximum fitness value. The maximum fitness value means that is giving best fitness. The fitness value will be generated from the fitness function. Okay. So what is the maximum fitness value generated from for a specific fitness function? So that particular encoding schema will be treated as a best rule. So something like that. So once we generate the rule, so the first step. So how the rule generation process here? It is a little bit different rule generation process. How that is takes place. First, you will take whole data set. So this class, suppose this class is something like yes, all are same. So it means that so first you will apply the spider monkey algorithm SM rule minor. So it will generate one rule R1. Right? It will generate one rule R1 and the class label of this rule number is yes. Rule is R, class is yes. Now, so what we have to do? Next you have to modify your data set. Because you have to prepare a new data set in which the tuples which are being satisfied by this rule, whichever satisfied this rule will be eliminated and created a new data set. In this, we will eliminate tuples satisfied by R1. So this is where modify the data set. Now again, you will apply the SM rule minor or any rule minor to generate the new rule. This is called R2. Once you generate the R2, you have to update the data set. Just generate the rule, then update the data set. How we will update the data set? By eliminating tuples satisfied by generated rule. So that's what we did here. See, so once the SM rule selects the rule, it updates the training data set or the data set by eliminating all of the records covered by that rule. Right. So this updated data is used to generate the next rule in the next iteration. So this is how the rule generation process takes place. So this process is repeat until we reach the some stopping criteria. So what is the stopping criteria? So the stopping criteria could be, so once the size of your training data set will fall certain threshold. Suppose if it is the number of records in your modified data set is below 10, then you can stop your algorithm, something like that. So this process is repeated until the stopping criteria are met. The size of the data set falls below certain threshold to obtain the desired rule sets. Okay, means so from the whole data set, first you will apply the SMO, the spider monkey rule algorithm or spider monkey based optimization algorithm to generate the rule R1. Once you generate the rule R1, you will update the data set to generate the rule R2. So this process you have to repeat until you reach the certain threshold. And so once you reach certain threshold, so your process is done. Means you will generate multiple rules from the specific data set. So if you clearly observe in this diagram, so this training algorithm, so once we take the training data set, so we have segregated on the basis of the class. So if you see, this is a negative class rule and positive class rule. And to generate the negative class rule, you have to apply the negative class, apply on the negative class data. To generate the positive class rule, you have to apply this algorithm on the positive class data. So once you do this on the positive and negative class, so this process you would repeat for, so the number of how many number of times you have to repeat for every class you have to repeat multiple times. So this process is same process repeat for the other class data too. So once you're done, so you have to combine all the rules which are generated from the positive class or S class, the rules which are being generated from the negative class. Then you can create the rule set. So like this, we can generate the rule set, and of course, you have to at the last you have to do the comparative analysis how the rule set which is being generated from this bio-inspired algorithm is when compared to the state of the art, what you call the rule generation techniques called C4.5, ID3, and all this stuff. So see, right. So what are the fitness functions? I mentioned the two important steps in any bio-inspired algorithm towards the solving any particular problem. So first you have to model it. So once you succeed in the modeling, then you have to choose the appropriate the fitness function. So that will evaluate the quality of your solutions. Okay. So the fitness function is very important. You have to carefully choose this fitness function. So what we did in the toward this end, but I am interested in a fitness. I am interested in what you call the rules that should be more accurate as well as the more compact. Means they should be the size of the rules should be as small as possible. At the same time, we should not compromise on the what you call the performance of these rules on unseen data called test data. So for that, what we have chosen uh, the fitness function that will balance both the positive class data and negative class data. So what we did, so we have defined the fitness function as a combination of three measures like geometric measure and mean interval rule length and comprehensibility. So for this, what we did, so geometric measure, there is a geometric mean of mean of um, geometric measure positive class and geometric measure negative class, and then we know how to find the geometric measure of the positive class is the geometric measure of the positive class is calculated using the recall. These are some of the performance measures which we frequently used in the classification algorithms. So I think you already know about this some stuff about. So I'm not discussing what is the recall and precision, but these will denote the how your classifier performance toward the positive class. And similarly, to evaluate the performance towards negative class, what we do, so we will take this inverse precision and inverse recall. I mean, so that will evaluate the how we have the classifier performance towards your negative class data. So basically, we are considering the performance toward the your classifier, how it is behaving toward the positive class, negative class, because we want to balance both. So then we have used these geometric measure of the positive class and negative class, and we have given some weighted average, something W1 into geometric measure of positive class and W2 geometric. So that will take place. You see, this geometric measure will combine the performance towards the both positive and negative class. Means we want to generate a rules which will perfectly balance both class data. That is important, right? Now, the same end, it not only what you call balance the both first and next class data, we should also generate what you call the comprehensive rules. To generate these comprehensive rules, what we did, we have introduced a concept called comprehensibility. So how we measure the comprehensibility? The comprehensibility of the rule is generated by the number of attributes in the root antecedent part divided by 1 second, and the maximum number of attributes in the rule cell. So why you have taken -1? Because if a rule is having 1, so in that case 1 minus 1 it will 0. Okay, something like. See, So to identify the best fitness function, we have considered the fitness function which will balance both our positive class and negative class data, and also to generate the comprehensive rules, we have taken the comprehensibility measure. So that will measure the compactness of the what you call the how compact is your rule. So to measure the compactness of a rule, we have used the comprehensive measure that we calculate using the total number of attributes in a rule antecedent part divided by the maximum number of rules in antecedent part. In our case, the denominator is 8 because we are taking a data set of dimensional of 8. Okay, so like this we have used. There is another what you call the mean interval rate. So what is this mean interval rate is I want to keep this interval range also as close as, so hence uh, uh, to generate the more what you call coverage rules, the more coverage area. So towards this end, what we did, we have used mean interval rate, and so this we calculated using by the what is the dimensions, what is the range of each and every dimension, and what was the lower and upper bound which were there in your rule generation. I mean, which was generated by your spider as a part of your encoding process, and how what was the lower and upper bounds were converged after the termination of your algorithm. So those we have taken, and we have compared, we have with respect to the maximum value of that attribute and minimum value of that attribute to identify the mean interval rate to keep this interval as small as possible, right? So then by depending on the performance of our choice, whether I am interested to create more compact rules, then I have to give the weight for W5 should be more, and if I want to create the more performance rule, they have to give the more weight for the W. This is based on the greedy approach. We have selected the weights for these W1, W2, and what are the weights I mentioned here. So because when we are doing the multi-objective, so we have to give certain weightage to each and every metric. So towards the which one you want to prefer. You want to create more performance oriented rules, you have to give more weightage to that particular metric, or you are interested to give it more compact rules, you have to give more weightage to that, or whether you want to create equal importance, then you have to give the equal weights to that, so that you will get the rules accordingly. So then so if you look at this particular the algorithm which you have chosen is a spider monkey, but you can choose genetic algorithm PS point. But every algorithm will have certain free parameters. Means why is this called free parameters or hyperparameters is because, as I mentioned, that we can solve we can solve many number of problems using bioinspired algorithm. So these parameter, the free parameters or the hyperparameters, have to fix it. You have to fine tune for this specific problem. So what we did for this, we can use some sensitivity analysis. So as we have multiple parameters, by keeping 4 parameters as a constant, and by changing the one parameter value and evaluating the performance of your model, then you can fix this value. So we did this process is called the sensitivity analysis. So like this, these performance plots were drawn, and so for which performance, for which particular value you are obtaining the maximum performance, so that particular value is taken as the optimal value for that, the best value for that particular hyperparameter. So this means that there are five performance plots are there. It corresponds to the fine tuning of the 5 performance the parameters. Okay, so once we done, so this we have to do for the both the classes, because this process you have to run for every class information. If there are 2 classes, you have to run for the positive class data separately and negative class data separately, rule generation process. Hence there are measures, this performance hyperparameter values are the specific to the data also. Okay? So you have, as we have taken the 2 class data, means the positive class data you have set up different set of values, and for negative class data you have different set of values. Okay, then so accordingly you also found, we fine tune the what you call fine tune the height of this weight values which were there in your fitness function using greedy approach. Okay, so this is so once we done the 10-4 class validation on the diabetes data, so we have generated some rules. If you see the sample for in the fold one, so you know what the 10 FCV. 10-fold cross validation, what we did, your data set is being generated, will be generated in 10 folds. So this is called fold 1. So this is called 1, 2, 3, and 10 partition. In the fold 1, what we will keep? The first partition as a test data set. The remaining 9 as a training data set. In the fold 2, the second fold will take as a test data, remaining 9 as a training, something like. So this is in the fold 3, fold 4, 4. So like this, you can address the class imbalance problem very effectively by using 10-fold cross validation. So like this, when you're doing this process, for one sum of the fold, we found that, you see, I took the how many number of rules were generated. Okay, so for negative class data, 3 rules were generated. For positive class data, 1 rule was generated. Togetherly, the rule set will have the 4 rules. And then what I did, what is the main rule length, MRL? What is the annual average? What is the length of the rule? That will measure the compactness of your rule. How we did? So for this, the total number of rules. So what is the number of attributes in each and every feature? So okay, there are 2 features. Here 1, 3, 4, 5, 6. There are 6 features in total. 4 out of 4 rules. So 6 by 4 is equal to 1.5. That way we found the main rule length. So this will measure the MRL, will tell you the on an average what is the length of your rule. So this is the towards the compactness, the comprehensibility of your rule, the number of rules and the size of your rule set, MRL and all. Now, if you look at the other the angle, the other way of the performance of your rules is you have to measure how accurately they are classifying your data. So toward this end, what we did, we found the accuracy and the other parameters called sensitivity and specificity too. But we found that after 10-fold cross validation, so nearly we got 90% of this SM, the spider monkey was generated the rules which are classifying your data with 90% accuracy. And of course, what is the after 10 folds, if you take the average value, so the on an average, the number of rules in our data is 4. And the rules size is average rule size 2. Okay. Right. And average, the rule set size is 2. So this was some of the results. Then, so as I mentioned, so we compared with respect to the state of the art algorithms. If you see the state of the ID3C 4.5 cart, then our proposed algorithm, if you see in the on an average, the ID3 rules, the average rules it is being generated is 6 and C 4.55, but cot is too heavy. The rule sets is nearly generating 100 rules, but our proposed algorithm on an average, the rule set size is size of the rule MRL, the average rule length will be is equal to the nearly 2. It's very we are able to generate very compact rules at the same time without compromising the performance in terms of accuracy, sensitivity, specificity. See the accuracy. So if you see the same problem which were solved using ID3C 4.0 code by building the decision tree, from the decision tree you are generating the rules. The same thing we are able to achieve with the help of the what you call bio-inspired algorithm, but at the same time we are able to get the good results. See, we are able to get very compact rules and also generating a good performance too, right? And so the same the performance has the same thing has been compared with respect to the what you call other bio-inspired algorithms too, like we compared with the artificial we call the PSO and anti-colony optimization, but still it is dominating in some sense, and like accuracy and sensitivity but specificity it is somewhat lagging. But as far as accuracy is concerned, it is very good. Okay, so we have this spider monkey generating very good rules, and in terms of both the performance as well as the compact rules. See, the important thing you have to observe here is you can model any problem. You can model any problem using bio-inspired algorithms, and so it is your duty to find the appropriate fitness function and how you are modeling your problem, how you are doing encoding mechanism. So that is very, very important. Okay. So once you are good at this encoding mechanism, you can map any problem to the any bio-inspired algorithm. So that's Right? This is some of the state-of-the-art comparison we made and all this stuff. Okay, and so this work we published in the one of the elsewhere journal and Computer and Biology Medicine in the year 2017. Okay, so that's it. And of course, still you can make what you call what we did. So if you observe, if you rule here, whether you observe or not in the rules over here, these rules are called crisp rules. If you see, the glucose is between 81 to 106. So the thickness between the 12 to 85. So that if these rules were something, they are very somewhat interpretable than your ANN based classifier, but still we can increase its interpretability by introducing some fuzziness into this, or some kind of what you call categorical values to these what you call these features, so that the readability or the understandability or interpretability of these rules will be increased. Okay, this is called a fuzzy rule. So we can still improvise this process in terms of the interpretability. Not I'm talking about the comprehensibility and accuracy, but I'm talking in terms of the interpretability. If you're generating more interpretable rules by introducing some categorical terms to these features, so then it becomes a fuzzy rule minor. Okay, so just I'm giving the glance over that. Then see how the rules which were we did that part also as a part of our PhD. So if you see, look at the rules over here. Okay, see if you see the rules is, this is called fuzzy rules, and these rules are very much interpretable than the crisp rules. Okay, just we have increased the interpretable, so that what will happen. So these rules are very important in some sense, because they are more interpretable than the crisp rules, and even people who don't have any background of your medical knowledge also can easily understand these rules. Suppose if your the BP is high, so everybody can understand. If I given the readings, if BP is between 140 to 180, I don't know, because I am not a medical background student. I don't know what is the readings of 140 means and 180 means. To bring more interpretability, so what we did, so we have used some linguistic terms, and so instead of representing in numbers, if you use some kind of a linguistic term like BP is high or BP is medium, that everybody can understand, right? So still we can use that kind of uh, uh, we can generate such kind of fuzzy rules. Okay, that we did using the BAT minor. Okay, so we have used some BAT algorithm for generating of such rules. If you look at the I will discuss only the important things over here is the fitness function as well as the encoding mechanism. So what we did, the encoding mechanism, look at it. So we have taken quadruple for each attribute. In the crisp rule we have used triple, but in the here we have used the quadruple. The first subfield will represent the flag, and the second subfield will represent the what you call attribute, and the third field will represent the what is the operator, because we have taken the operator and the value. What is the linguistic term? Suppose if you see, I have taken A1 is equal to medium, because it means that, what does it mean? What is the A1? What is the linguistic attribute is assigned to this particular feature and is equal to medium. So the medium is a linguistic term assigned. Whatever the operator we have used, we have to, instead of less than or equal to, greater than or equal to, because they are inappropriate when you are using this linguistic terms. So we have used different operators called equal and not equal. Suppose if A1 is equal to medium, means something BP is equal to medium, something like you can interpret this. Okay, that is the way we have encoded this particular problem using this quadruple, and we have used the different what you call the fitness function over here is. So what is the fitness function we have chosen is rule coverage. The rule coverage means how many number of tuples are being percentage of rules, how many number of tuples are being covered by a given rule, and antecedent coverage. What is the antecedent coverage? So the antecedent coverage will measure is calculated dividing number of features in the rule and antecedent per the dimension of the data. So the antecedent coverage will be towards the crisp rule. We want to get the crisp rule. The rule coverage will be towards the more coverage will have more performance. So the first part will be taking care of the more towards the performance. We want to get better performance. At the same time, we want to minimize the length of the rules. So that's why it's a multi-objective. So that we have used the minus because we want to maximize the rule coverage. We want to minimize the antecedent coverage. But overall, we want to minimize and maximize. So overall, you have to the maximize. Okay, the fitness has to be the overall. The fitness function has to be the maximize. The feature which is having the maximum fitness value. The set of the encoding the encoding part which is having the maximum fitness value will be treated as a best the rule fuzzy rule for your problem. So like this, the rule generation process is similar to the earlier one. The only the encoding process has been changed, and the fitness of course the fitness function is also changed. Except those two changes, the remaining process is same. Okay. So today I explain how we can model a problem using bio-inspired algorithm toward the what you call a rule generation process, and so how we got a good results when compared to the state of the art by using this bio-inspired algorithms. Okay, with this I'm stopping my session, and if you have any queries, you can put it now. Okay, so still 10 minutes are there for your queries, and you can ask any queries.
Sir,
Yes.
am I audible, sir?
Yes,
Okay.
yes.
Sir, I have a question. So, like in classification rule mining using bio-inspired algorithm, do we require a lot of training data for this? Hello?
Yes, yes, yes.
Yeah, and this is one question. Other one is, what is the future scope in this area, sir?
In this area means you are talking about bio-inspired algorithms, or you are talking about classification rule generation?
Both, sir. Both.
The bio-inspired algorithms you can apply to any domain. Okay, if you take any NP-odd problem, and you can address it using very cleverly by if you have a good encoding mechanism, good fitness function, and good hyperparameter tuning. If you ensure that this proper parameter tuning, proper encoding mechanism, proper fitness function, you can get a the reason why people are using this bio-inspired. You know what is the NP-odd problem, right? The NP-odd problems will require a lot of computational resources, and it requires huge time. If you want to get the solution for this, you have to wait for the days and days, and it is very computational intensive. Of course, you require huge computational resources. But the same problem, suppose if you take the rule generation process, but you can solve this problem very quickly, but with a little bit compromise on your solution. You may not get the optimal solution, but you will get the near optimal solution. That is the main agenda of you introducing this soft computing techniques or introducing bio-inspired algorithms is to address the most of the NPR problems in a less amount of time. So it means that if you have any NPR problems, you can cleverly address using any one of the bio-inspired algorithms. And one more thing is there is a concept called no free lunch theorem. So what it says that there is no global algorithm for all your problems. Suppose,
so please repeat, sir.
So yes, let me finish. Suppose if the spider monkey is working for the diabetes data, but it may not work for the other data. So there is no global. If it is working for this, it may not work for others. So you have to fine tune your problem. You have to fine tune the algorithm. You have to fine tune the hyperparameter. You have to identify suitable. So this is the kind of research. Okay, so you have to, it's a task of your programmer to identify suitable algorithm for a suitable problem. So there is no global algorithm for this. So there's a huge scope, and if you take any, suppose tomorrow a new algorithm may come, and it may overtake your spider monkey algorithm. You may get better results on this.
Okay, sir. Okay, so thank you, sir.
And if as I mentioned, your data, so of course, if your data is there, definitely you can. Thing is, if there is a huge data is there, suppose if there is a huge data is there. Suppose you are talking about if there is shortage of data, maybe we cannot ensure the performance, but it takes very less amount of. The data set is huge. Obviously, this process also become very tedious, because you have to generate the rule from all the data, right? So you have to scan each and every tuple from all this data. So you have to, it takes some time. Okay, so we cannot guarantee that if there is scarcity of data, can we ensure about the performance? So because it all depends on, okay. So it as I mentioned, the no freelance theory will talks about that. Okay, unless until we experiment, we cannot comment anything on that.
Thank you very much, sir.
The still scope is there because I think what is the performance here, the gap we found us. Okay, so let me check the what was the performance we got. So we got only 89. Still scope is there. You can improve up to 94, 95, 96. Still scope is there. I don't know. We can improve it by using other algorithms. Yes. No problem.
Okay, sir.
Yes, guys, if you have any doubts, and the modeling is important, selecting suitable fitness function is important. Yes, ma'am. If you don't have any query, then I'm stopping my session. Okay. Thank you. Bye.
Thank you, sir. Thank you for enlightening us. Thank you so much. As participants, the next session will be at 2:10. You all please join to the next session by 2:10 exactly. And again, I'm saying you please rename your IDs with the IDs assigned to you, which is posted in the WhatsApp group, even in the chat box also. Thank you.
Just a small.
Hello, ma'am. Anupriya, ma'am.
Yes, sir. Tell me.
Ma'am, this my ID is from my college. I can't change my name. This is
Achha.
given by, this is my college ID. How can I change this ID's name, ma'am? I can't change.
You have logged in with your college ID, sir.
Yes, this is my college ID, Vardhaman ID, which I am working. This
Okay, okay.
is my college. I can't change.
Okay, okay, sir.
I
Okay.
guess so many people was there. They can't change their ID names.
Achha, okay. I'll see that, sir. I'll see that issue, sir.
Okay, ma'am.
Thank you, sir.
Madam, this is Dr. Prakash.
Hello, ma'am.
Yes, sir.
Hello.
Yes, sir. Tell me, sir.
What about the feedback link? Will it be for each and every session or will it be for a day?
No, sir. Every session, sir, will just forward in the WhatsApp group, sir.
Okay, madam. Fine.
Okay,
Yeah.
sir.
Thank you.
Yes, ma'am. Tell me, ma'am.
Ma'am, can you please send the ID list again in WhatsApp group?
Yes, ma'am. Yes, we'll forward.
Okay, thank you. Thank you, ma'am. Thank you,
Okay.
ma'am.
Hello, ma'am.
Yes, sir.
Ma'am, Priyanka, this side chat box is not enabled to me over here.
Achha. Ma'am, have you joined in the WhatsApp group, ma'am?
Yes, I have joined over there.
Okay, we'll forward even in that also.
Okay, sure. Thank you.
Okay. I request all the participants once again now, please join in the WhatsApp group using the link. And if you have any issue with the tiny URL, you please go through the detailed URL which is posted in the chat box by Lavanya ma'am. Okay, thank you. Thank you all. You please join back by 2:10. Thank you.